Okay, maybe we can start. Okay, so good morning, everybody. So welcome back to this second lecture. So first of all, you can find on the screen a QR code. Please scan it. It's not the menu of the restaurant. It's the list of the exercise of yesterday that you saw yesterday. So here you will find a drive folder where you find the PDF of the theoretical exercise and also the numerical exercise, not the notebook, right? So okay, so are there questions about yesterday's? So okay, yes. You can also find the folder where you can upload your solution of the exercises. So, did you have time to think about yesterday? No. Okay. So for the exercise, of course, feel free to come both in the, let's say, in the office hours, but also outside the office hours if you want to discuss about the exercise or also other stuff related to gravitational waves, cosmology, future life, and so on. So yesterday, so we um, stopped at um, we stop with the linear Einstein equation. Okay, so let's write it from. Okay, we linearize it. Okay, so we wrote our metric as a flat matrix plus a small perturbation with the condition, the weak field condition that assume that this fluctuation must be smaller than 1. Okay, so we linearized the Einstein equation and we realized that naturally fixing the Lorentz gauge and the residual gauge, they emerge 2 degrees of freedom. Okay. We didn't specify very well the degrees of freedom, but we understood that this tensor mode, this tensor perturbation carries to these 2 degrees of freedom. Okay. So in a moment, you will realize that we will realize that these 2 degrees of freedom are essentially the 2 polarization that in GR we have for the gravitational waves. Okay, so we are in GR, we are not beyond GR where you can have more than 2 polarization. So if you linearize, if you take the Einstein equation, you linearize, you arrive at the wave equation. Let me still write in terms of the trace reverse matrix that in absence of any source or very far from your source, it's a wave equation. Okay. So and as you know, it has a wave-like solution. So what we will do today, hopefully faster than yesterday. So it will be the extension of these in the case of in the presence of a source. Okay. Because in the case of a presence of a source, it's not easy to distinguish between the background and the gravitational wave itself. Okay, so we have to introduce the concept of gauge invariant quantities, and we will find a wonderful properties of gravitational waves that at linear order, these guys are completely gauge invariant. So they already are physical degrees of freedom. So I will give you probably also some tips about what is a gauge transformation. So then in the second part of the lecture, so we will compute, no, yes, in the second part, we will compute the Einstein equation on a curved spacetime, on a Friedmann-Robertson-Walker metric, and we will see how the equation of motion for gravitational waves emerge in a curved spacetime, and we will solve the Einstein equation, and we will find the solution for that you saw in the exercise yesterday in the on the super horizon regime and in the sub horizon regime. And then we will do an example of this in a, let's say, in an inflationary setup. We will see the first cosmological model that could be relevant for interferometers. Okay, so this is the summary of yesterday and a spoiler of the lecture of today. So I will not do the calculation properly, but when you fix the residual gauge and you choose, let's say, your vectors chi mu, such that box of k mu is equal to 0, okay? So you are also satisfying, so if you remember the lecture of yesterday, so this property here. So if you satisfy this property here, so you can do a bit long calculation, but you realize that you have the gauge freedom to choose what is the trace of the trace reverse metric equal to 0, okay? And also the component of the metric H mixed equal to 0, okay? So if you have the freedom to choose these, okay, first of all, so you have the first property is that your trace reverse metric coincide exactly with the initial one, okay? So while using this second condition, what you realize is that so if you take your, if you want your Lorentz gauge, okay, you put equal to 0, so you can see that this is okay. I assume that you are all familiar with the tensorial manipulation, okay, with Summit indices, okay. So this is yes, this is equal to 0. So since we have done this choice, okay, so this means that D0 H00 is equal to 0, okay. So this means that if you want H dot 00 is equal to 0. Okay, what this means, because this could be a problem to understand why we have just 2 degrees of freedom. So we have essentially that the 0, component of my tensor perturbation is essentially our classical Newtonian potential. So it's a static function. Okay, H00 is a V of x. Okay. So this means that gravitational waves, this clarifies that gravitational waves, this h, let's say ij, are the only two propagating degrees of freedom, okay? The h00 does not propagate. So now, if we combine all the information that we discussed yesterday, we arrive at the most used gauge when you work with gravitational waves, okay? So you put together the condition h mu 0 equal to 0, trace of h equal to 0, and di hij equal to 0. So you put everything together and you obtain what is called the so-called transverse traceless gauge, or TT gauge for the friends. So why this is very important? So if you, okay, this means that my tensor mode is transverse. Okay, this is the condition of transversality. This is condition of being traceless. Okay, so this is the condition that we put thanks to the residual gauge freedom. So let's see what this means. So we had, you remember that we had this 4x4 matrix, okay? So we, okay, since we have the transversality condition, okay, we can assume that, let's say my gravitational waves, okay, propagate along the z-axis, okay? So this is reasonable choice, so you don't lose any generalization, okay? So this means that all the components of hij along the z-axis are essentially 0, okay? So this means that all hi3 are equal to 0. So this means that here we have 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so, and this is what we are left with. Now, let's think that we have also the symmetry condition, okay? So if this is symmetric, so this means that A12 must be equal to A21, okay? And also you have the traceless condition. That means that H11 is equal to minus H, okay, is equal to H22. Sorry, I made a bit of, okay. So you can write H plus, H cross, and minus H plus, okay? Where I have defined, okay, so H plus and H cross equal to minus H22 equal to H plus, and H21 equal to H21 equal to, sorry, this is H cross, okay? So, and these H plus and H cross are the two polarization of gravitational waves, okay? So this comes from the symmetry condition, and this this comes from the traceless condition, and this comes from the symmetry condition. Okay. So I think that now you, if you want, you have everything to write what is your polarization tensor in the TT gauge. Okay. So essentially, my transverse traceless gauge fix all the gauge freedom, and you just have two physical degrees of freedom that are the two polarization of the gravitational waves. Okay, so, and you can also find the form of epsilon plus and epsilon cross. So now let's complicate our life, because in flat so when you don't have a source, okay, or you are very far from the source, so you have seen that the right hand side is equal to 0, okay? So now let's include the right hand side, let's include this source, okay? I can write h mu nu because they are the same, okay? So we are still in a flat space-time, okay? So this is still my Minkowski metric. I still have to impose my weak field condition, okay? So this h mu nu must be small. What is the main topic? What is the main problem here? Is that when you have a source, okay, when you have this energy momentum tensor, so it's not easy to distinguish between what is a gravitational waves and what is my background, okay? Because remember that in this case, okay, I will tell you later. So in this case, yes, you the energy momentum tensor on the background has some properties. Okay, so what you typically do when you have a situation like this, okay, is that so essentially you apply the scalar vector tensor decomposition. So SVT, okay. So essentially what you do, you split your take advantage of the SO3 group, okay, and you look how the metric perturbations. So remember that here we have 10 degrees of freedom at the beginning. So you look how this metric perturbation transform under SO3, okay, or and you what you do, you introduce a set of scalar perturbation, a set of vector perturbation, and a set of and the tensor perturbation, okay. So, and you see what is the equation that drives this perturbation. So, so I will use a strange notation, not the usual one. So it's probably better if you use some standard references like for the perturbation like May-Bershinger and so on. So here I will be a bit mixed up. So if you do this splitting, you see that delta G00, okay, that is essentially my H00, is equal to minus 2 psi delta G 0I. Tell me if you are all familiar with this. This is a vector, and this is the tensor part. Okay. Okay, don't need to confuse this. Minus 2 phi delta ij plus di dj minus 1 delta ij okay. So this is these are my scalar perturbation psi. So phi, beta, lambda are the scalar ones. Okay, so you have 4 perturbation. Then you have the vectors. Okay, and then you have also beta I and epsilon j, and then you have the tensor hij. Okay. So what is the, I didn't show how this transform under a gauge transformation. If you want, we can see later. So in total, so you have 4 scalar, 4 degrees of freedom that are of vector type, and 2 from the tensor type. Okay, so you have 10 degrees of freedom. So what you do, you impose some condition, okay, on the vector and on the tensor. So you, okay. Okay, so you have the condition that your vector is transverse as well is traceless, and also, okay. So, and the main point here is, instead of working with fixing a gauge as we have done before, so the idea is to build what are called gauge invariant quantities. So, meaning that all these quantities, since they are gauge invariant, they are physical, okay? But let's see if they propagate or not, okay? So, if you do a bit of mathematics, okay, you realize that this is capital psi, okay? When I write like this. If you write this combination, so if you do the gauge transformation of the metric perturbation, and then you do this gauge combination, okay, you realize that this capital object, okay, this is a condition. What matters more is this, okay? So you build your gauge invariant quantities. This is a scalar, this is a scalar gauge invariant quantity, this is a vector gauge invariant quantities, okay? So, and this is a tensor gauge invariant quantities. So, and you realize something very nice, okay? That your tensor modes, your tensor perturbation are gauge invariant per se, okay? So, you do, they don't transform under gauge transformation. What you do now is you compute your Einstein equation because you have everything, right? So at least on the left-hand side. So you compute your Einstein tensor component, okay? I do this calculation because it's a nice properties when we will go in curved space-time, okay? Okay, sorry if I went below. So what is the an advantage here? So the point is that we should do the same transformation also on the right hand side, right? So but there is a nice properties uh, um, for the right hand side that we can use. So since we are on a flat space-time, okay, so you don't need to write your gauge invariant quantity on the right hand side. So what you do, so you consider that your energy momentum tensor should transform like this, okay? So, but this guy, okay, is zero on the flat space-time, okay? So essentially, there is the so-called Stewart-Walker lemma that allows you to say that your gauge invariant quantity are essentially set by the energy momentum conservation. Okay, so you set from here, you derive from here what are the gauge invariant quantities, the physical degrees of freedom. So, and if you do the calculation, so if you apply this, okay, so you get okay, you decompose your energy momentum tensor, delta t 0 0 equal to rho, delta t 0 I equal to du plus y, delta t ij equal to p delta ij plus di dj minus 1/3 delta ij sigma plus so the most important quantities that you have to take into account here is this pi ijtt, okay, that is the transverse traceless part of the anisotropic stress, okay. This is very important because so if now I compute the Einstein equation, so I have everything to compute the Einstein equation, I have the left hand side and I have the right hand side, okay. So I can compute my Einstein equation and arrive to something like this, okay, in terms of my gauge invariant quantities. Rho. Okay, So these are my the set of my equation that describe by my metric gauge invariant quantities, and you realize something very important. So you realize that for the first three gauge invariant quantities, so they have a Poisson-like equation. Okay. While for the tensor perturbation, it is the only one that has a wave-like equation, so is a propagating degrees of freedom. Okay. So that's you realize two important properties. First of all, that my tensor perturbation is gauge invariant by itself. Okay. And the second thing is that the only propagating degrees of freedom. And the third thing is that this anisotropic stress, okay, that I have still not defined how to extract it from the energy momentum tensor, is a source for gravitational waves. Okay, this is very important when we will study interferometers, because essentially we will see that if you solve, so I don't want to spoil everything, but if you solve this guy, okay, as we will see, will be the propagating equation of gravitational waves in whatever space-time, in a curved space-time, in a Friedmann-Robertson-Walker matrix. The signal, the solution coming from here cannot be seen with interferometers, at least the one that I listed yesterday, okay? So you need, in some way, a source for gravitational waves. So when I mean that you need a source, okay, this source is, I will describe better and we will go in details. So this is what I called extension of inflation, okay, inflationary setup, okay, could be a source, could enter in this, let's say, source part. The phase transition, okay, and in particular first order phase transition. So I will not describe, but you can imagine that in the phase transition there are some fields that source the tensor perturbation. The topological defects, what we call the cosmic strings, among them one of the most studied is cosmic strings. So they also act as a source of gravitational waves. The mechanisms are a bit different, so you should be careful. But the idea is the following: that they are source for tensor perturbation. And what I told you yesterday that becomes very hot in the recent year, the scalar induced gravitational waves. So you will realize something very wonderful when we will solve the Einstein equation in a curved space-time. You will see that the scalar, but also the tensor perturbation, source the tensor perturbation. Let's focus on the scalars because you get confused, but otherwise. So, but you will see that when we go to second order, okay, so this guy will be second order. So here you will have a source that is done by the product of two first order equations. But you don't need to do any trick because you can already see something here, okay? More or less. Now we will see better when we go in curved space-time. So, but you will realize essentially from the spatial part of the Einstein tensor. Okay, so this concludes the part on the flat space-time. Let's move in our universe away, and let's go in curved space-time, okay? Because the cosmological setup that we have is a curved space-time. Everything is okay? Are there questions? Okay. One of them is multi-field. Okay. For instance, you can have also. We will, if you want, we can do an example of this. So what I mean with the extension is, for instance, having a gauge field together a scalar field. Okay, so in principle, so if you have a coupling between, okay, let's write this as a function. Okay, I didn't say if this is a the inflaton or not. Okay, you can realize now. So if you have a coupling like this, okay, for instance, and you compute the energy momentum tensor of these guys, and you extract the transverse traceless part, you will see that these guys act as a source for the gravitational waves. But you can have also other kind of extension if you want. So multi-field is another example. So let me think. What are other situation? So you don't need even to add the other multi-field, but you have to relax a bit some symmetries. Yeah, the simplest example is this one, when you couple your inflaton field to an extra field. In this case is a U1 gauge field, but you can also think to an SU2 field. And yes, this is the simplest example that it comes in my mind. Other questions? Yes, please. We are still in the weak field approximation. So, and here we are at first order, and everything is independent. Okay, so you don't mix scalar vector and tensor. So when we will go to second order, so there will be these nice properties that I was telling you. Here, yes, I didn't specify, but these are all first order perturbation. Yes. Okay. Other questions? Okay. So let's build our cosmological setup. Okay. So the situation when we will move to a curved space-time is very similar to this one. Okay, so the situation is completely similar. Okay, so the only difference that complicates the life is that now, so you really don't know so how to distinguish your gravitational waves from your background solution. Okay, so because in principle also gravitational waves carries energy. Okay, so in principle how I can distinguish the part of the energy momentum tensor due to the self interaction of the gravitational waves to the presence of the matter around. Okay, so this is not it's a long calculation if you want to do properly. So you have to expand both the left hand side and the right hand side at second order. Then you have to combine them, you have to define pseudo energy momentum tensor and so on and so forth. So it's quite long, and I think that you can find on several books that explain better than me this part. But also it's quite long, so I thought that was not the case because it's not the main focus. Because so as soon as you realized that you can build these gauge invariant quantities, but even more, so as long as you introduce what are called separation of scales, okay, this simplifies your life. Let's see what this means. Okay, so we are in a curved space-time. Okay, imagine that we are in a Friedmann-Lemaitre-Robertson-Walker. Okay, expanding space-time. So, and let's introduce what are these separations of scales. Gabriele already introduced yesterday a bit. So let's just add a couple of small words. So you have your metric perturbation, okay, that will be, so in this case, this is not Minkowski anymore, okay? plus delta G mu nu of x, okay? And the condition that these are small fluctuation, we will see how we properly define gravitational waves, also in curved spacetime, is important, okay? So now the main point is, okay, you have these background quantities. When I put a line on top, so this is a background quantities. These background quantities varies on length scales that I call LB, okay, length background, okay. While let's go straight to the gravitational waves, it varies on some wavelength lambda, okay. So the condition that you need to impose to distinguish, okay, the gravitational waves, okay, here, for the background, that is this so-called separation of scales, is that your lambda must vary on length that are much smaller than the background, okay? So this is the condition that allows you to separate your gravitational waves, okay, from the background. So imagine that this is your background, okay? So and these are your gravitational waves, okay? So this is the separation of scale graphically, okay? So you need to decompose your wavelengths if you want your typical length of the background, okay? And the wavelengths of the gravitational waves. So in this way, you can distinguish the two, okay? So what is the main point here? So the main point is, okay, the main point is the following. So if you do this separation of scales, okay, so instead of doing the only the separation yes, let me add these two notes because it's very important. So instead of considering only this condition, because yesterday there was a question about this and I think that is important, so you have to consider also another condition if you want, because the gravitational waves on scales lambda means that it has a frequency that goes as 1 over lambda, okay? And the background that has this scale LB, okay, has a characteristic frequency that we call FB, okay? So the other condition that you need to put, if you want, is that besides this, another way to distinguish your gravitational waves is that your frequency, okay, must be much larger than the frequency of the background. Why I introduced this condition? I introduced this condition because, let's do an imaginary example. So when you consider the cosmological setup, it's very easy, okay? You consider the cosmological setup in which your background is essentially your Hubble horizon, okay? So, and you are quite, how to say, relaxed, because for sure the the condition of the separation of scales in the cosmological constant context is satisfied, right? So you cannot have something like that. So the situation is a bit different when you consider gravitational waves from a compact object. So in which, so you cannot say anymore this. So in which case, the wavelengths of your gravitational waves can be of the same order of the background. Let's see why. So you typically have, for ground-based detectors, so you typically have, if you want, frequency, as we saw yesterday, that are around 10 to the 3 hertz, okay? This means that you have wavelengths that are order 550 kilometers, okay? So, so this means that, so the situation here, it's not easy to distinguish the two. What is the main point? On top of this, you have that your potential, okay, is much larger. Your gravitational potential, that is of order 10 to minus 9, is much larger than your gravitational waves, because so we know that these are order 10 to minus 21. Okay, let's do this rough calculation. So you are a bit in trouble with this. But the solution is very easy, because what this is telling you, okay, is that to observe a gravitational waves with interferometers, so you need to set this condition. Where is it? F much larger than F background. What this is telling you, so this is the background, the frequency of your background coming from here. So this means that your frequency must be above the Newtonian limit. And if you remember what I told you yesterday, so when you go at low frequency, this calculation is valid for ground-based. So when you go to small frequency with gravitational waves interferometers, you have this wall given by the seismic, by the Newtonian noise. That's the reason why you need to go to high frequency, let's say high frequency, to frequency larger than your background, okay, here, to observe a gravitational waves. Let's do, okay. This is the simple explanation why you have this wall at small frequency. And why, so if you go in this regime, you can define what is a gravitational waves. So it's, yes. As long as we didn't detect gravitational waves in the 2015, we were worried about this. Now we are not worried anymore. So we can classify gravitational waves. Because in the CMB case, in the cosmological case, so the classification is very simple. So the situation will be, okay, I shouldn't erase this. The situation is much more complicated, but this is even more challenging. So, and we are working a lot on this, is when you, on top of your background, you add what are the so-called anisotropies of the stochastic background. In that case, the anisotropies, okay, evolve on these scales, while your gravitational waves evolves on these scales. So, and it's similar to the CMB. This is the same case of the CMB, right? So you have these long modes perturbation on which they propagate your photons. And when your photons or gravitational waves propagates on this background, they acquire what we call anisotropies. And this is what you measure in the map of the CMB, okay, if you want. And this is what we are building now to build some map of the gravitational waves, okay, imprinting this, let's say, information about the background. Let's do the calculation in curved spacetime, okay? So if we go on curved spacetime, so I don't think that I need to do all the calculations step by step. It's very similar to the flat spacetime case. So the only complication is that now, so you have a scale factor that you know, okay? So you have your metric. We have decided that this is a Friedman-Robertson-Walker matrix. So I use tau. Gabriele was using eta. They are still the same things. It's the conformal time. Okay. Each time that I teach, I change a letter. I don't know why, but okay. So this is my background metric. Okay. I can perturb my metric. I will simply write in this way. Okay. I have added, okay, it's not completely right what I wrote here, but you can understand. So I added a small perturbation on my background, okay? So tau is the conformal time. This is just to tell you, yeah, that's the reason why, but there is this one now, okay? You know that Minkowski is conformally related to, Friedman is conformally related to Minkowski. So you can, the important thing is the scale factor. So I introduced this because if you want to do the gauge transformation on curved space-time, it's easier to do in this way, okay? So, and whenever you will see something like this, a prime, this is a derivative with the respect to the conformal time, where the dot is the derivative with respect to the cosmic time. Okay, scale factor. This describes the evolution of our universe. So, if you do exactly the same step as before, so now you should be careful because your perturbation transform like this. Okay, two warnings. One is the presence of the scale factor, the other is the presence of the covariant derivative. So you are in a curved space-time, so now you have something like the partial derivative plus the Christoffel symbol. Much longer calculation. Okay, but you can still also in this case build your gauge invariant quantities. Okay, I just write this because I think is symmetric, right? It's mu nu nu mu is symmetric. Yes, this is plus. Now it's symmetric. So okay, so the very nice properties is that still in curved space-time, these guys are still gauge invariant. And what I introduce here are the very famous Bardeen potential, okay? That everyone that goes out from the school theoretical aspects of cosmology, astroparticle should know, okay? So saying that, so you still can perform a gauge transform, a gauge fixing. So, and if you do the gauge fixing, so you arrive at the form, at the general form of the matrix in curved spacetime. Okay, let me write here. Okay, so you have the most general perturbed first, okay, matrix in a curved spacetime, okay, with the scalar, vector, and tensor perturbation. So now you should consider that when you lower and you raise your indices, you should be careful because there is this scale factor that enters in your mathematics, in your tensorial manipulation. So if you do the same steps as we did in the first lecture, okay, now you have everything to compute your Einstein equation. So this is the last GR equation that I show. Then we will move to the interferometers. Okay, so yes, okay, delta, okay, delta Gij, okay. Okay, see what happens here. Okay, I put okay, anyway. Okay, so if you look at this equation, so at the Einstein tensor, so you realize that there is the equation of motion for your gravitational waves, okay, where now you notice a factor that we will understand soon, that is the conformal Hubble radius, okay, Hubble factor, that is A prime over A, okay, that essentially is telling you that you are in a expanding universe, okay. So these gravitational waves that evolves in our universe feel a kind of friction from the universe itself. And this is telling us that it's very important to understand the regime in which you are and also where these gravitational waves are propagating, okay? And then another nice property is that you cannot see at first order, but it's already a flavor or what happens when you will go to second order, okay? You can also start from this and perturb this. It's easy, easy. Okay. You go to second order. At second order, gravitation tensor and scalars are not independent anymore. So I don't want to confuse you. So I see people with the okay. So but when you will go at second order, okay, you will see that these scalars, okay, you bring them to the right hand side, and they become a source for the tensor fluctuation, right? So you have realized, for instance, that simply in GR, okay, so you have the box Hij that is sourced by some terms like di phi, dj phi, okay? I just write these two. I don't do the calculation. I will do, if we have time, this. So you see, naturally in GR, scalar perturbation becomes a so-called source for scalar perturbation. But this is a bit advanced topics. You will see. What I want to stress here is that now we have the equation of motion. So and you have the other scalar perturbation. So now that we have everything, okay. So we can write the equation of motion for the gravitational waves, considering also the right hand side. So, and the situation is very similar to the previous one. Okay, so if you write your equation of motion in curved spacetime, in expanding spacetime, so you have the following: Hij prime prime. So I don't write the TT, but we are always in TT. Let me write before in real space. let me write this in TT because otherwise you get lost. Okay, but these are all TT. So again, so expansion of the universe now that we haven't seen before, okay, and source for the gravitational waves. So what I will do now is the following things. So I will solve this equation in the next 10 minutes without considering this source, okay? So to do that, okay, so okay, will be the situation where I will solve it. You can easily extend this to the case of a source, but so the simplest thing is to solve this in uh, in the sourceless case. For curious people, so when I say that the TT part, because probably you are not familiar with it, so this is Sij, sometimes is indicated in Fourier space, okay, with pi Lm, okay. So to extract the transverse traceless part from the Einstein equation, you need to apply this projector, okay. This is a combination of okay, let me write. So PIL, okay, PJ L, okay, minus 1 IJLM minus 1 half P IJPLM, okay. So this is this projector where this Pij is delta Ij minus Chi Kj. So whenever your supervisor will ask you to extract the transverse traceless part from some equation, you apply this projector, okay. You can find it uh, everywhere, and it's easier to apply it in Fourier space. Yes, please. Please, please. Uh-huh. From? Yeah. Yes. Yes. What, so the point, so we will, if you want to, okay, sorry, I canceled it. So at the end of the day, so this is the same things that comes from, uh, okay, so you can take also your Einstein-Hilbert action, okay, you perturb this at second order, you vary it, and you obtain the equation of motion. It's the same story. When you want to connect this, okay, to the tensor part, remember that there is, okay, there should be something there. Okay, so you can also start from here and you arrive here. So let's solve this equation in in two regimes. First of all, so I did it in okay. Okay. So I want to find a solution for Hij. So the first thing that I do, I go to Fourier space and I do this redefinition. That simplifies my life. Okay, this is K and tau. Okay. So remember how I decompose this Hij, as we have written yesterday, this Hij, so is the sum over the two polarization, the integral, the Fourier transform, Okay, so I apply the Fourier transform to this, and uh, I introduce this. I rescale this variable. Okay, so if you do this, so your equation of motion will be the following. Okay, right? Okay, so this is your equation of motion in Fourier space. Let's solve it. So the easiest thing is to solve this equation into regime. Okay, because remember that we are in an expanding universe. Okay, so the universe, this gravitational waves propagates, but the universe expand. Okay, so the solution, so of course, as I was saying, will depends on the epoch in which this gravitational waves propagates. Okay, so let's assume a general power law for the scale factor, where this is equal to 1 for radiation, this is equal to 2 for matter phases, and this is equal to -1 for the Sitter. Okay, okay. So, and now let's go into regime. One is the sub-horizon regime, where this k is much smaller than h. Okay, or if you want, k tau is much smaller than 1. Okay, this means that your wavelength is much larger than your Hubble radius. Okay, so you are on sub-horizon. Okay, on sub-horizon, sorry, we are doing sub-horizon. Okay, this is k tau much bigger than 1, and this is k much larger than h. Okay, sorry. Yes. H, because this is in Fourier space, as you know, so you don't need to do this. Yes. Okay, so sub-horizon regime. So in this sub-horizon regime, essentially your gravitational waves as an oscillating solution. Okay, so your equation we reduce to h prime double dot k tau plus k square hp of k and tau, and this equal to 0. Okay, so in the solution will be the following. Is exactly the one that Gabriele wrote yesterday on the blackboard. So the most important things to realize is that when you go to sub-horizon, your gravitational waves decaying with time. Okay, so this means that this is your horizon, this is your gravitational waves, so they are decaying as 1 over a. Okay, so now instead let's go to super horizon scales. Okay, this is the typical setup when you consider inflation, for instance, that stretch your fluctuation on super horizon scales. So when you go on super horizon, k much smaller than h. Okay, this means that k tau is much smaller than 1, and lambda is much larger than my horizon. Okay, okay, in this case, so the solution, the equation, so you can neglect the k term, so this means that the solution becomes the following. Okay, and the solution is the solution will be the sum of a constant solution, as you know, plus a decaying solution. Okay? So when you go on super horizon scales, so when this is your horizon and your gravitational waves is much larger than your horizon, so if you want, in this usual plot for, let's write time, okay, let's write A, okay, that you typically see in your cosmology course. So here, okay, there is inflation ends, okay. Modes that are here are subhorizon, super horizon here, and subhorizon here again, okay. So this means that when they are here, your gravitational waves acts as a constant, okay, here. When it goes here, it starts to oscillate with this solution, with this solution there, okay, and it starts decaying inside the horizon, okay. So in this regime here. So then, so you should also consider that up to here, up to the equivalence, so here we are in a radiation domination phase, okay, and here we are in a matter domination phase, and we are here at GGI, okay. So then you have to consider also the fluid where these gravitational waves propagate. So the behavior in radiation and in matter is different, okay. So I think that this is all the let's say what we need now to do the computation with the interferometers, right? So everything should be more or less clear, I hope. Are there questions? Yes. This? Yes, is double. Huh? This. You have to. Yes. Yeah, but you have to take these guys, okay, okay, and you have to write yes, yes. This is a double prime. It's correct. No, no, it's not h. It's the derivative of h. So yes, because or this thing. So if you take h and you take this is a prime over a. So you take the derivative of this. There is a first term here that goes like h, and then there is another term here that goes as h prime. So here this term is negligible with compared to this one. So you just consider with this one and you put this much smaller than h part. This one, okay, we should understand also where this gravitational waves propagates. So if you have the sitter, for instance, when we fix the behavior of A, okay, this guy is 0 because H is constant. So here is general. I didn't specify any phase where gravitational waves are propagating. I'm just saying I am subhorizon, I am super horizon, I am subhorizon here. Okay. The next step is fixing my evolution stage. Okay, my evolution phase. Okay, let's assume that we are in the sitter as you want. Okay, and let's solve this equation. Okay, and then we can compute the power spectrum of these guys. So I want to connect the primordial universe with the interferometers today. This is something that you don't find on the book. That's the reason why I like to do it. So to do this, yes, we need to fix this stage. Yes, and let's do it. Are there other questions? No, I don't know if is everything is clear or you get lost. Okay, so let's do this job. Other questions? No. You can do it in the meantime. So I was thinking to, uh, yeah. Uh-huh. This is h to minus 1, this guy. This the most important things of inflation is that it allows to shrink your Hubble horizon, and you're co-moving here, and your fluctuation can go. So here you set your scale, right? Whatever scale you want. So assume that you want a scale lambda, call it star, okay? This is your scale. So during inflation, what happens is that the Hubble horizon shrinks, okay? Yes, because I'm, yes, exactly. Uh, and These guys goes outside the horizon during inflation. Then inflation stops. These guys at some point re-enter the horizon. I assume that you are more or less all familiar with this. Uh, no, no, no. This is the co-moving one. Yes, this is the co-moving one. Okay. Other questions? No. Okay. Uh, let's do this exercise. Or no, let's do another thing. So let's do in this remaining half an hour, go straight to the definition, go through the definition that Gabriele told you yesterday. I want just to do a couple of simple of assumption, because then it's easier, as long as I introduce you the spectral energy density of gravitational waves, the characteristic strain, is easier to connect to the power spectrum, okay? What I want to do, uh, and I will finish tomorrow, is that you take your inflationary model, okay? You compute your power spectrum, let's call it P of H, okay? So from here, you arrive here, okay? Because when we do the measurement, we are here. So, and this is not simple. So you need to take into account the fact that gravitational waves evolve here, evolve a bit here, okay? So this means that connecting, let me write it in this way, connecting the primordial power spectrum with what we observe today, this 0 means today, or more properly, the right quantity that we measure with interferometer is this guy. That means that the Hubble parameters time my spectral energy density. But let me do a step behind, and let me tell you a bit of general stuff about stochastic background. Because now you have the solution, okay? You have your modes function. So as I told you yesterday, all the stochastic background are characterized by ensemble averages, okay? So the ensemble averages that you have to perform are ensemble averages on this guy here, okay? So let's go, and let me explain this. So we already says, okay, that we have a big picture of this stochastic background that is splitted, if you want, in two main sources: astrophysical background and cosmological background. So the astrophysical one, it's easy to understand because it's the incoherent superposition of all the sources that you observe, okay? So you look at all the sources, at some point your resolution of your detector is limited, you are not able to distinguish anymore among the different sources. In the cosmological case, you have to think about in a quantum, you have to think in a quantum way. So because as soon as you realize that all the stuff that I described before are quantum fluctuations, so this means that they are stochastic. So, and if they are stochastic, the only way that you can use to characterize them is through ensemble averages. So everything is qualitatively. Let's do a quantitative statement, okay? And let me tell you what stochastic means. So it means that the amplitude of your gravitational waves, that is again the sum of the plus and cross polarization, okay? It means that the amplitude of my gravitational waves polarization is a random variable, okay? That can be characterized only through ensemble averages. Okay? Yes, but you know, and you can tell me, but I don't have many universe. Okay? I have just one universe. So how do I do these ensemble averages? What you do, I never remember if you're, okay? You take advantage of the ergodic theorem, it's the same things that you do also for the CMB, and you exchange this ensemble average with some space or time averages, okay? So what you are saying is that I look to my object many times, okay, or for a lot of times, okay, and I essentially exchange my ensemble averages with my with some spatial or time averages. So what this means? This means that when I did my separation of scales, okay, when I did my separation of scales, okay, I need to sum over many wavelengths that are between these two limits that should be expected, okay, to distinguish your gravitational waves. And the same thing, you can do it on the frequency, okay? So you have to average many times to build what is an ensemble averages. So, but there is some things that help us when we look at the interferometers, is that you more or less you know what you are looking at, because the stochastic background has some, if you want, some first order approximation properties that allows you to simplify your life. So you expect that your stochastic background, and in particular the cosmological one, is quite isotropic, okay? It is a small perturbation on an isotropic an isotropic metric, the Friedman matrix. So you expect that at first order, if you want, is isotropic. The second assumption that you do is that it is stationary. Okay. So this means that your signal will never depend by an absolute time, but will always depend from a difference of time. So, and if you go to Fourier space, if you want, this means that in your signal there should be a delta of your f minus f prime, okay? Then you expect that your gravitational wave background is unpolarized. So I will not discuss polarized stuff. This means, okay, this means that if you compute, okay, there are two ways to tell you this. The easiest is that if you compute the correlator of H plus H cross is 0, okay, but this it's not easy to do. The other thing is that you start from epsilon plus and epsilon cross. You build the chiral basis, okay, that is 1 over square root of 2 epsilon ij plus minus plus epsilon ij cross. You build what is your chiral basis. That is the right basis to look at if your gravitational waves is chiral or not, and you compute the power spectrum, okay? I have not explained you how to connect the power spectrum with h square, but for the moment, let's assume that this is your power spectrum. They coincide, okay? And you compute your left power spectrum and your right power spectrum, okay? And you will see that they are the same. This means that my stochastic background is unpolarized. If they are different, and it could be different, this means that it is polarized. The last approximation that we typically do is that my stochastic background is also Gaussian. So if it's Gaussian, okay, why it's Gaussian? So in the case of the astrophysical sources, it's easy to understand that it's Gaussian, okay? In the case of the astrophysical sources, it's easy to understand because the central limit theorem, if you want, says that more source that you have, more your signal is Gaussianized, okay? If you want, the distribution looks like a Gaussian. In the case of the cosmological case, it's a bit less immediate, but since these gravitational waves propagate from the early universe, so in the process of propagation, they dephase, okay? And this means that if you compute the 3-point function, okay, this is 0. So this last assumption of Gaussianities, okay, is essentially setting us all the properties to define my my correlator, okay? So I told you that I need to define my 2-point function, and it's enough because it's Gaussian. So I don't need, when I mean non-Gaussianity, it means that I don't need anything above the 2-point function, okay? Yes, please. Okay. In which, in the scalar sector or in the tensor sector? Mm-hmm. Okay. Okay. Nice question and long answer. So the point is, what you have to, you don't, the situation is different from the CMB, okay? So the point here, when you compute the non-Gaussianities, is that you have to remember, in the case in which you do on H, because the subtlety is this, I don't have time to discuss, but if you compute the non-Gaussianities of H, this is 0. So if you compute the non-Gaussianities of the intensity, the easiest thing to think is that is the modulus of H dot square, okay? This is not 0, okay? Okay, it's a long explanation, but it takes this into account. So if you compute the non-Gaussianities of this guy, this is different from 0. But the main point here is when you average. So is the average, is the way in which, in this case, we intend ensemble averages, okay? That in some way kills this signal. Because you have a limited time where you integrate over your detectors while your signal is accumulating a lot. If you want, I should write here T, that is the time of integration of your detector. That's the difference with the CMB. So, did I reply more or less? So I can give you a paper on this. So if you do, if you trust in my assumption, okay, this is a factor that will be clear soon. This okay, this is okay. This is delta PQ. That is the translation of unpolarized. Okay. Then you have a delta 3 of K minus Q. Okay. This is the isotropy plus the stationarity. Okay. And then you have what Gabriele introduced you yesterday, that is what is called the characteristic strain. Per logarithmic interval. Okay, two important things. The first thing is that it is only a function at this stage of the modulus of k. Okay, it's not does not depend from the direction. And in a first approximation, this is due to the isotropy that we assume. And the second important thing is that these normalization factors, okay, if I remember well, it comes from the fact that when you take the real space yes, HP star, is it? What is it? Yes, no, okay, sorry. When you take these, dk over k over hc square, okay, so it comes from we want to have these two, that is the sum over the polarization. Okay. Okay, this is the reason why we choose conventionally the factor 8 pi to the 5. Of course, it depends on how you set your Fourier transform and so on and so forth. So the important thing is that this guy, HC, is a dimensionless quantity. This is what people in the gravitational waves community likes to describe the gravitational wave signal, okay? So, yes, okay? And this is the same things that you see also, for instance, in the LIGO-Virgo collaboration, is the same quantities, okay? And essentially is a characteristic, if you want, gravitational wave value of the amplitudes of a gravitational per unit logarithm. Oh, amplitude per unit logarithm. Yes, you see here. Okay. Okay. So why, I derive this? because this is a d log k. Okay. So this characterize your stochastic background. So whenever you have your model, you have to compute hc square. Okay, you have to compute the power spectrum and you have to extract hc square. So if you do this, okay, for instance, you can do it for resolved sources, and you can do for the stochastic background. Okay, if you want, you open when you will open the next time the web. Okay, and you will look plot like this. Okay, this is 10 to minus 12. This is 10 to minus 16, 10 to minus 18, 10 to minus 20, 10 to minus 22. Okay, so you will see, for instance, that PTA, okay, has a noise like this. Lisa has a noise like, okay, I didn't, 10 to minus 9, 10 to minus 6, 10 to minus 3, 10 to the 0, 10 to the 2. Okay, so Lisa is here. Okay, and here you have LIGO. Okay, more or less. So you will see that, for instance, your stochastic background, so we have not computed any model, but has a characteristic strain like this. Okay, so you understand now what this means. So this is the main aim of this lecture, to tell you, to let you understand when you open a plot like this. So this is the noise of PTA, one of them. This is Lisa. This is LIGO. Okay, and what you do, you compare your characteristic strain that now we will relate to the spectral density to the noise of your detectors. So if this is above, okay, this is the qualitative picture, your signal can be detected. Okay, so here, for instance, you can also compute the characteristic strain coming from stellar origin black hole. Okay, you would find that they should have a behavior like this, or you could even find the characteristic strain of the stellar origin black hole for LIGO. Okay, and you find this is the shape of your characteristic strain. Okay, so if you want to play a bit, there is an online tool that is called GW Plotter. It's better if you build by yourself, because this is not very, okay, it's registered. But you can plot the characteristic strain versus the frequency. Okay. Now, so I don't think that I need to do all the details, because you did in the exercise. The next, in the final minutes that I have, I want to connect this characteristic strain, my power spectrum, to the other main quantities that we typically use to characterize a stochastic background. So, and these are, okay, these are, okay, so the gravitational waves energy density, okay, so you did it yesterday, okay. This is 1 over 32 pi j a square h prime ij h prime ij. Okay, in reality, yes, h prime ij. Okay, so this is equal to the integral between 0 and infinity of dk over k d rho gw over d log k. Okay, so you did the exercise, so you know that now you can define the next important quantities, that is the gravitational waves energy density. That is essentially 1 over rho c times the, okay, the logarithmic derivative of the energy density. Okay, so remember that is related to the T mu nu, T00, rho C today is 3 H naught square mass Planck square, okay? And if you do the computation right yesterday of the exercise, and you plug your solution for your mode function inside here after having Fourier transform Hij, and after having considered, this was the trick that Gabriele didn't tell you, that Hij is a real function, okay? So you should consider that this is a real guy, okay? So when you include the stuff, this is a real guy. So this gives you the properties, some properties of of HP and also epsilon ij p, okay? That you should be careful, okay? So if you do everything correctly, so you will find that your gravitational wave spectral energy density has the following form. So I took it from the book, I didn't do the calculation, okay? So this is should be the solution of your problem, okay? And finally, because you were asking yesterday why we introduce another quantity, okay? It's not our fault. It's the gravitational waves community, okay? And what we introduce is the strain spectral density, okay? That is this SH, it will be clear in a moment, HC square of F over 2F, okay? So you are telling me why you are introducing another quantity to confuse ourselves, okay? Because when gravitational wave people that build interferometers and they study a lot the noise, okay? And they characterize a lot the noise, okay? What they will give you is not omega, but they will give you what is called Sn, okay? That is the power spectral density, okay? That has a dimension of h to minus 1, okay? This n relates to the noise. This h relates to the signal, okay? Yes? Sorry? Ah, you are saying this. Ah, this is, yes, sorry. Yeah, this is, yeah. Yes, yes. Great. No, thanks. It seems you are very at them. Okay, so they give you this. It's good that you are so waked up. They give you this. So because they measure all the noise in your detector, right? So and they transform in these units. So what we will see tomorrow, okay, at the end of the lecture, is that your SNR will be proportional. I'll take it for now in a brute force. Will be proportional to the ratio between your signal, your strain spectral density that is related to your model, okay? Remember there, inside HC squared, there is your model, over the noise of the detectors, okay? That's a matter of convention. So in our case, where we work on stochastic background, okay, so we typically do, and this is uh, the final part. So what we typically do is working with omega GW, okay? let's say that is 0 today. That is essentially a redefinition of this quantity. Okay, so at the end of the day, you can pass from one to another consistently. Okay, just redefining them. It's just a matter of redefinition and a matter of convention of different communities. Okay, so we try to homogenize with the gravitational wave people, detector guy, the one that do the hard job. Okay, that extrapolate characterize the noise. So while we are more familiar to work with omega, because as we will see tomorrow, okay, sorry if I go left and right. So this is this omega GW today, okay. Let me write proportional is what is called a transfer function, okay, times my let yes times a primordial power spectrum, okay? So you take your favorite primordial model, so let's take that you like axions, you compute your power spectrum for the axions, okay? So you tell to these guys that they have to propagate from, let's say, when they exit the horizon, okay, up to today, and all the information of their journey is inside here, okay? And I will tell you I will give you the form of this transfer function, because this essentially allows you to connect the early universe with today, okay? Yes, please. Okay, so it depends, okay? So if you like to be in single field slow roll inflation, okay? So you know the power spectrum is the Fourier transform of the 2-point function hk. Okay, let's write it in this way. Tomorrow we will be more accurate. Okay, so as I told you yesterday, this is proportional to this. Okay, as long as so it could be a power law. Okay, so if you compute this guy in single field slow roll inflation, okay, you will get something that is called the consistency relation, okay, that tells you that these guys is equal to minus 60, okay, is proportional to epsilon, okay, that is the slow roll parameter, okay, and this epsilon is order 10 to minus 2. This is a parameter that characterizes inflation, for instance, as you probably know, okay. This means that this is essentially negligible, okay, in single field slow roll inflation. What is the trick? So the trick is essentially the following. Just give you a spoiler of tomorrow. So I'm working in omega. I'm not working in H anymore. So here you have the CMB. Tomorrow we will do it carefully. Okay. Here you have Lisa. The trick is, if this guy is 0, so you have something like a flat signal. Okay. So the trick is that when you include the source that I was mentioning before, so it happens that your signal is not flat anymore. So it has an NT that is different than 0. Okay. But to do this, you need to extend inflation, single field inflation. Okay. And this will be the lecture of tomorrow. Yes. Questions? Other questions? Okay. We are a bit fast in this last part, but the main, yes, I give you the main. No questions? Sorry? Yes. Yeah. Why? Uh, no. Why? So this is the Hij that you have there is also when the first time that we introduced was Hij there, right? In the you mean in the flat space-time is where we define Hij that are H plus and H cross. These are the gravitational waves. But stochastic in the sense that today you measure these guys, okay, and you measure the 2-point function of this guy that is proportional to your omega. This comes from there. Probably I didn't get your answer, your question. So the meaning stochastic is that okay, in the cosmological case it borns as stochastic because it's quantum. Okay, in the astrophysical case it becomes stochastic because it's an incoherent superposition. Okay, I don't know if this reply to your answer, but so when it borns, it doesn't born as omega GW, it borns as H, okay? Then it's perceived as a stochastic background, okay? What you measure today is a stochastic background because during the propagation, all these waves sum incoherently, okay? And what you will measure today in your detector looks like, if you look at your data stream, looks like a white noise, okay, where there is this stochastic signal. I think that this was the second part of the lecture where I introduced. It's not really related to, let's say, to. So the first part was important to tell you how gravitational waves emerge in GR. Okay, so yes, and then yes, how they form a stochastic background. So, but if you have two black holes, okay, tomorrow we will do this calculation. So, but you have many of these two black holes, you can also form a stochastic background. But this does not mean that they born stochastic in the source. Is it clear? The stochasticity, if you want, enters when you do the ensemble. That is the way, the time. So they born stochastic, but the real point is that you need to do the ensemble averages, right, to measure it. Other questions? If not, let's stop.